Chapter 4, Section 5 talks us through graphing using the slope-intercept form of a line. So let's read the key concept. A linear equation of the form y equals mx plus b is written in slope-intercept form, where m is the slope, b is the y-intercept. So I wrote this out, y equals mx plus b, and if we look at this example, y equals 1/3 x plus 1, the 1/3 is the coefficient of x. It's sitting in the same spot as the m. So if I were to graph this line, the steepness of the line, or the slope, would be 1/3. The y-intercept, where it crosses the y-axis, sits here at 1 because it's my constant. It is the number that is being added to my x term. If a number was being subtracted, that would just make my y-intercept a negative number. I'm going to apologize quickly for this. It should actually be written over there. But let's look at our example. We have y equals 3x plus 4. The coefficient of x is 3, so that's sitting in the spot where my m would be. So that must be my slope. And the y-intercept is 4. In my second equation, I have 3x plus y equals 2. Well, this is not written in the form y equals mx plus b. One of the big indicators is the fact that my y term is not isolated on one side of the equation. So I'm going to come over to the side of my paper, and I'm going to start this problem by rewriting it to get it in slope-intercept form. To isolate my y, I need to subtract 3x from both sides. I would be left with y equals 2 minus 3x, but we know that we want that x term to be written first, so I'm going to write this as negative 3x plus a positive 2. In this form, it will help us see that our slope is 3 and our y-intercept is 2. So what does that actually tell us about a graph? I'm going to click over to Desmos, and we're going to take a look. Y equals 3x plus 4. We identified our slope as 3 and our y-intercept as 4. I just want to take a second and prove it to you. When I typed it into Desmos, you can see the red line is being graphed. Let's prove that our slope is indeed 3. To find our slope, we're going to pick two good points. Point -1, 1 is a good point to plot on our graph. It's a good point because I can give the exact coordinates without getting involved in decimals or fractions. Another good point on my graph is the point 0, 4. If I were to count from -1, 1 up to 0, 4, and I were to count my rise, remember what you're looking at. The scale is actually a half. I'm moving up 1, 2, 3 units, and so that would be a positive 3, and I'm moving to the right 1 unit. That's my rise over my run, proving that this number right here is our slope. Where does this line hit our y-axis? It hits our y-axis right here at the point 0, 4. That's where this number is coming into play. Let's go back to our notes. I've referred multiple times to the 3 methods of graphing. So far we've talked about the table method of graphing, using intercepts to graph, and finally we're going to talk about how this information that we know about the slope-intercept form can help us make a graph, I'm going to say in under 15 seconds. So let's take a look at the equation that's given. It's obviously not in slope-intercept form because y is not isolated. So let's take a second and rewrite it. 2x plus y is equal to 3. I want to isolate y. Subtract 2x from both sides. Y sorry about that, y equals negative 2x plus 3. So step 1, rewrite the equation in slope-intercept form. Negative 2x plus a positive 3. Next, we need to identify the slope in the y-intercept. So my slope is going to be a negative 2, and my y-intercept is going to be a positive 3. The third step is to plot the point that corresponds to the y-intercept. That is going to be the point 0, 3. I know my y-intercept always hits on the y-axis, so my x-coordinate will always be a 0. So let's go down to our graph and actually plot that point, 0, 3. Now we're going to use the slope to locate a second point on the graph. My slope was negative 2. I'm going to write that so that I can clearly see my rise and my run. If it is negative 2, I can always put negative 2 over 1 to create a fraction. I think writing it this way will help you to actually translate this into a graph. If my rise is negative 2, I'm going to move down 2 on my y-axis. If my run is a positive 1, I'm moving over 1. I can do that a couple more times. Down 2, to the right 1, down 2, to the right 1. You can see, without knowing the coordinates of these points, that it is clearly forming a straight line. So let's graph that line. I should be able to travel from one point up 2 and back 1, and continue to hit points along my line. The last example that we're going to talk about is using what we know about slope to identify parallel lines. So here's what this example is asking us. Determine which of these lines are parallel, line A, B, or C. Obviously, I think that you can take a look at these and make a pretty good guess that A and C are parallel. But we're going to set out to actually prove it, to prove that our instincts are right. So let's start by looking at line A. Can we find the slope of line A? Well, let's look for two good points. I would say that the point negative 1, 2, 3, 4, negative 2 is a good point. I'm going to kind of write that over here, negative 4, negative 2. And I would say this one right here, negative 1, negative 1. So let's find that slope. I'm going to use a blue pen. Remember, my y coordinates go in the numerator, negative 2 minus 1. My x's go in the denominator, negative 4 minus negative 1. When I subtract in my numerator, I'm going to do same change to get a negative 1 over a negative 3 or a positive 1/3. Let's look at line B. Two good points on line B. I would argue that is a pretty good point. Let's see, that's negative 1, 2, 3, 4, 5. Negative 1, 2, 3, 4, 5. So for line B, the point negative 5, negative 5. Let's find another good point on line B. This looks pretty good. That's the point 0, negative 1, 2, 3. Let's subtract our y coordinates in our numerator. Negative 5 minus 3, minus a negative 3, and negative 5 minus 0. In my numerator, I end up with a negative 2, and in my denominator, I have a negative 5. That simplifies to a slope of 2/5. Let's look at our last line, line C. Finding two good points. I would say this looks like a pretty good point. That would be negative 1, 2, 3, 4, 5, negative 6. Another good point on that line, I would say this won't be a pretty good point. Negative 2, negative 1, 2, 3, 4, 5. For line C, let's subtract our y coordinates, negative 6 minus a negative 5. In my numerator, negative 5, my denominator, negative 5 minus a negative 2. We'll end up with negative 1 over negative 3, which reduces to a 1/3. Let's take a look at our slopes. For line A, I have a slope of 1/3, line B, a slope of 2/5, and line C, another slope of 1/3. That should back up what we thought originally, that line A and line C do look indeed to be parallel. If we have two lines with the same slope, we know that they are increasing at the same rate, or they have the same steepness, therefore they are parallel. What I'm going to ask you to do now is to refer back to your notes and try the guided practice questions that you see up on your screen. If you printed out the copy of the notes, then you should already have this sitting in front of you. I'd like you to press pause, do a couple of problems, and then hit play to check your answers. If you have questions, write them down and ask me in class. Here are the answers for the guided practice problems. For problems 1, 2, and 3, you can see the answers are circled. Hit pause if you want to take a look at my work. We're going to scroll down to look at the graph for number 4. You can see that this was my original point plotted. That was my y-intercept. I went down 2 and to the right 1 because that was my rise over my run to plot my next point, and then I drew my line in. Finally, number 7 asked us to see which of these lines were parallel. I found the slope for all of those lines and determined that line A and C were parallel because they had the same slope. Again, if you have any questions, please write them down and ask me in class.